Hey, what's up, Algebra 2? It's Ryan. Today we're going to be working on graphing rational functions. So, rational functions are pretty much a staple of any Algebra 2 or pre-calc curriculum. And it's important to understand, some of their characteristics and how they'll behave. So, hopefully, over the course of today's lecture, you'll become a little bit more familiar and comfortable with graphing these type of functions. Okay, so let's first start with domain. So that word has come up at various times throughout the school year so far, but essentially that's the range of possible x values where y is defined, right? And so one of our cases where y is not defined, and this comes up a lot in rational functions, pretty much every time in rational functions, is where our denominator equals 0, right? Because we can't divide by 0. So what value of x gives us makes our denominator 0 in this first problem? 3. So we know that this is going to be, we know that x, cannot equal 3. And depending on the teacher, you might be able to just say x cannot equal 3, or you must say, all real numbers, but x cannot equal 3. And this is the symbol for all real numbers when you combine that right there. Okay, so in this case, what value can x not be? Well, we just need to set this equal to 0, and we'll just see pretty quickly that I'm just going to move this, or you know what, I'll write this out. Equals 0, we move that 7 to the other side. And then we divide by 2, and we find out pretty easily that x cannot equal 7 over 2, or 3 halves. Right? And then in this case, we have to factor this, right? Or we should factor it. So what two values add to -3 and multiply it to -4? Well, that's going to be x minus 4 and x plus 1. And right, this is going to be equal to 0. And so what values of x make this equal to 0? Well, it's going to be x cannot equal 4 and x cannot equal -1. Okay, perfect. Now let's move on to here. So first of all, what is a rational function? It's basically a function in the form of p of x over q of x. So we have two different functions and we're dividing the two. And as we said before, q of x can't equal 0 because then f of x isn't defined. So that's why we have these domain restrictions, right? And so when we have when we have these domain restrictions, when when f of x isn't defined, we'll have these things called asymptotes, which are basically, well, no, it isn't just when f of x isn't defined, but essentially we'll have these lines in rational functions that where our function sort of approaches each of these lines, these imaginary lines, but never actually touches it. So that's the definition of an asymptote, places on the graph that the function will approach but never actually touch. So for example, we have this vertical asymptote going up and down, and this part of our function gets closer and closer to that line but never actually touches it, right? And it goes on for infinity. And likewise, down here, we approach this line but we never actually touch it. And so when we're graphing these rational functions, we want to know these vertical and horizontal and even slant asymptotes, because that's going to help us get a better picture of how these rational functions behave. Okay, so we're throwing a lot of information at you right now, but I'm going to read through this, and then we're going to put this into practice. And hopefully after we put it into practice, you'll understand some of what I'm saying right now a little more. Okay, so first, whatever you want, the first thing you want to do when you're sort of graphing these rational functions is factor. So if you have, say, a quadratic or a cubic, you want to try, or pretty much any polynomial, you want to factor those, maybe factor out a constant if possible. And then once you have factored forms on both the numerator and the denominator, you can compare them and see, say for example, we'll see this in some later cases. If we're multiplying by the same thing on the top and the bottom, say x minus 2 and x minus 2, we can cancel those out. And that's going to basically elicit the same function, but we're going to have whole at x equals 2 because we canceled out x minus 2. We'll talk about that a little bit more later. And it's fine if you don't understand it right now, but once we put it into practice and we see a case where that comes up, hopefully you become a little bit more comfortable with it. The second thing we want to do is find the zeros. So essentially, the way we find the zeros, right, the zeros are our x-intercepts. So essentially when y equals 0, and y equals 0 when our numerator equals 0. So we want to set our numerator equal to 0 and solve for the values of x that give us that y value of 0 and graph those. The next thing we want to do is find the vertical asymptotes. And so that's sort of what we did up before, where we set our denominator equal to 0 and then solve. And then we also, the next thing after that would be to find the horizontal asymptotes. And there's some rules with this. So first, if all of this centers around the degree of the numerator and the degree of the denominator and sort of how they compare. So our first case is where our degree is greater in the numerator versus the denominator. And so in that case, there is no horizontal asymptote. If that happens, we're going to go down to 5, which I'll actually just explain right now. And that means there's going to be a slant asymptote. So in that case, we're going to have to do some division. Okay? And so we're going to have to use some of our long division skills we covered earlier this year, and possibly even our synthetic division. Okay? Our second case, and so slant asymptotes, as opposed to, vertical asymptotes, go like this, as you'd expect, running vertically. Horizontal, go like this. And then slant, as you'd expect, go at an angle. Okay, so our second case is if our degree of the denominator is greater than that of the numerator. And in that case, the horizontal asymptote is just y equals 0, which is just the x-axis. Our third case is if they have the same degree on both the numerator and the denominator. And in that case, what we would want to do is take the leading coefficient of the numerator and the denominator and divide the two. We're going to see all of these cases in the examples we do today. And so that way you'll get a little bit more comfortable and see how we'd graph functions in rational functions in each of these cases. Okay, so obviously 5 would be to find the slant asymptotes. This is pretty much only true in case A. But it's only true when the degree of the numerator is 1 more than the degree of the denominator. So in this case, actually, I'm going to go back on what I said. Essentially, if the degree of the numerator is many degrees higher than that of the denominator, there's just no horizontal asymptote. But you do want to, if it is 1 more, you definitely want to reference this one down here. And then our last step is some rational functions will have a y-intercept. If there is a y-intercept, just replace x with 0 and then solve for your y value. Okay, so, and then for the actual graphing part, we would want to, draw the vertical and horizontal asymptotes, plot the x and y intercepts, and then pick certain x values to sort of get points and, figure out what that graph looks like. Okay. Yeah. Okay. Great. Now, let's start with our first example. Okay. So, the first thing we want to do is factor, right? And so I'm going to factor this function. I'm going to call it f of x. F of x. And how we factor this is I'm going to do this to this side. We have 3x squared plus 3x minus 18. Now, there's a bunch of different ways to factor quadratics that have an a value greater than 1 or different than 1. But the way I do it is I multiply my a and c values. So what's 3 times negative 18? Well, that's just going to be negative 54. So I think of what are two values that multiply to negative 54 and add to positive 3. So if I'm just going through that in my head, sorry, give me a second. Let's see, if we have, no, it's not 4, 6, for example, we'll see. 6 times 9 is going to be 54. Sorry, that took me a second. It's all right. Okay, so we're going to say 9 and negative 6 add to 3 and multiply to negative 54. So instead of saying plus 3x, I'm going to say plus 9x minus 6x minus 18. And this is the same thing as our equation up there. And so in this case, I'm going to sort of, and instead of saying minus 6x, I'm going to say plus negative. Okay, if that's all right. And I'm going to put each of these in parentheses. And then at this point, I'm going to do factor by grouping. So what's the greatest common factor out of this first parentheses? Well, that's going to be 3x. And what are we left over with? X plus 3. And then what's the greatest factor we can take out of negative 6x minus 18? That's going to be negative 6. And then we're going to be left with x plus 3. And so at this point, we have the same parentheses here. So we can rewrite this as 3x minus 6, x plus 3. And actually, in this case, I'm going to factor out a 3. We probably should have done that at the very beginning. That would make this entire thing a lot easier because we wouldn't even have to go through this. But it doesn't matter. I should have been more careful. But we end up at the same answer nevertheless. Okay, so let me just make sure. This is 3 times x minus 2, x plus 3. Okay, great. I believe that's right. Yeah. And then on the denominator, what can we factor out here? Well, we have x and then x plus 3. Okay? We just factor out an x out of that. And we notice pretty quickly that we have an x plus 3 up here and an x plus 3 down here. So in that case, we can cancel out both of these from the numerator and the denominator. And that's going to give us this function. 3 times x minus 2 over x. And now these two functions are going to behave pretty much exactly the same, but the only difference is going to occur at -3, because we're still graphing this function, right? We're still, because this function is our original function. But we, at -3, it's not going to be defined, right? Because we multiply, when x equals -3, we have a 0 here, and so everything, no matter what this is, multiplied by 0 is 0, and same for the bottom. So we're going to have 0 over 0, that's undefined. Whereas here, we can plug in -3 and be totally fine. So what we want to do, and I'm just going to do this right now, is plug in -3 to this function and find what that is and put a hole on our graph. So when x equals, and I'm going to do this in a different color. Feeling very colorful today. Oh, sorry. Oh, I'm not really going to say f of -3. I'm sorry. But say we just plug in -3 for x. We're going to get, let me put this in. Well, -3 minus 2 is -5. So 3 times -5 is -15. And then this is going to be over -3. And so -15 over -3 is just going to be +5. So that's going to be our y value. So essentially what I'm going to do is I'm going to say a hole right now. I'm going to put this in blue. I'm going to say our hole is at -3, 5. Okay? And what I'm going to do is at that point, which occurs right here, I'm going to have an open circle. Okay? And I know that our function is going to go through this point, but it's not actually going to be defined at -3. Okay, so our second step, if we go back up here, is to find the zeros. And so that means setting the numerator equal to 0 and solving. So what value of x makes our numerator equal to 0? It's just going to be 2. So our x-intercept is going to be 2, 0, right? Because we plug in 2 here, 2 minus 2 is 0, 3 times 0, 0 over 2, 0. Okay, now if we go back up here, sorry, I keep on going back up. Now it's to find the vertical asymptotes, and that's what we did before in setting the denominator equal to 0. So when does our denominator equal 0? At x equals 0. So we're going to say our vertical asymptote is x equals 0. And our vertical asymptote is a line, so I'm just going to say x equals 0 because that's going to be our imaginary line, as opposed to just saying 0. So this means our domain is going to be all real numbers except x cannot equal 0. And again, it depends on who your teacher is. They might want you to say all real numbers except for 0. They might want you to put it in interval notation. That sort of varies from class to class. Now we want to deal with our horizontal asymptote. And so in this case, we want to look at the degree of the numerator versus that of the denominator. In this case, our degree of the numerator is 2 because we have that 2 right there. And our denominator, it's also 2. So we have the same degree on the numerator and the denominator. So we want to scroll back up and see, what do we want to do in that case? Well, that's going to be case 3, or case C, where we take the leading coefficient of the numerator and divide that by the leading coefficient of the denominator. And that's going to be our horizontal asymptote. So we want to say our horizontal asymptote is going to be y equals 3 which is 3 over 1, because we're multiplying that x squared by 3, multiplying that x squared by 1. So that's just going to be y equals 3. So our horizontal asymptote is y equals 3, range y cannot equal 3. Perfect. Now we want, so we've dealt with our vertical and horizontal asymptotes. Our degrees for our numerator and denominator are the same. The degree of the numerator is not one more than the denominator. So we know there isn't a slant asymptote. And now we want to see if there's a y-intercept, and if there is, what that y-intercept is. And so we find that y-intercept by plugging 0 in for x, and we see pretty quickly that we can't have that because we have a domain restriction at x equals 0, which is along that y-axis. So this does not apply. Okay, so we have a bunch of information. And at this point, I'm going to graph the asymptotes. Okay, so we have a vertical asymptote at x equals 0. So that's going to go along this line right here. And then we also have a horizontal asymptote at x equals, or y equals 3. So I'm going to go right here. Sorry. And now we want to graph some of the points we have. So we have 2, 0 as a point. So I'm going to graph that right there. And then we already have that hole. So at this point, what we want to do is just plug in a couple of points and see what we get. So I'm going to use our equation up here. So let's plug in x equals 3 to get a point right here. Or actually, let's do 4. So 4 minus 2 is 2. 3 times 2 is 6. 6 over 4 is 1.5. So at 4, we're going to have a point right here. Now let's plug in a point for x equals 1. So 1 minus 2 is negative 1. 3 times negative 1 is negative 3. Negative 3 over 1 is just negative 3. So we have a point right there. And we start to see something that looks like this start to form. Okay? And when I'm drawing this, notice how I'm getting close to the asymptote, but I'm never actually touching it. Okay? Now let's do this upper left-hand portion. Let's plug in negative 1. So negative 1 minus 2, negative 3. Negative 3 times 3 is negative 9, and negative 9 over negative 1 is going to be positive 9. So I know we have a point up there. Okay, now let's plug in something like let's do negative 4. Or actually, sorry, I'm just thinking about this. Let's do negative 6. But yeah, it doesn't matter. Okay, negative 6. Negative 6 minus 2 is negative 8. Negative 8 times 3 is negative 24. Negative 24 over negative 6 is positive 4. So I know we have a point right there. And again, we start to see this, our shape, start to form. And so it looks something along the lines of that. Okay, with that hole at negative 3, 5, right? Because we're still graphing this function. It just can simplify it to this, but we still have to include this information because x plus 3 still provides valuable information. And that it tells us that we have a hole right there. Okay, so our graph is going to essentially look like this. Okay, let's move on to the next problem. So we're going to do the same thing. Our first step is to factor. So how do we factor the numerator? We want to find two numbers that add to -1, multiply to -12. So we're going to say, I'm going to call this f of x again. It's fine. We're going to say f of x equals, and our two numbers that add to -1 and multiply to -12 are -4 and 3. So we have x minus 4, x plus 3. And then we can factor out a -4 out of the denominator. So we get -4 x plus 1, right? Or sorry, x minus 1. Jeez, I'm sorry about that, y'all. Boom. Okay. So now we want to find the zeros. The way we find the zeros are by setting our numerator equal to 0. So essentially first actually, let's look at this. Can we factor or cancel anything out? No, we can't, so we don't have any holes. Now we want to set our numerator equal to 0. So what values of x make our numerator 0? Well, that's going to be 4 because of this parentheses and -3. So we're going to say, 4, 0 and -3, 0. Perfect. Okay. Now we're going to find our vertical asymptote. And that's by seeing sort of what we're setting our denominator equal to 0. So what value of x makes our denominator equal to 0? 1. So we have a vertical asymptote, x equals 1. So that means x cannot equal 1. And that's our domain, all real numbers except for 1. Now we want to move on to our horizontal asymptote. And so we want to look at our degrees again. Well, what's our degree of our numerator? That's going to be 2 because of that exponent. And what's our degree of our denominator? That's going to be 1 because it's x to the first. And so our degree of our numerator is greater than that of our denominator. And so let's look up here. Well, we have that satisfies case A. And so that means there is no horizontal asymptote. But we want to look down to number 5 and see, is our degree of our numerator 1 more than that of the denominator? And it is, right? We have a degree of 2 and then a degree of 1. So that means we want to divide the 2 and find what we call the slant asymptote, which is this right here. So let's do that. Okay. So we have, or you know what, I'm going to do this off to the left here. We're going to do sort of what we did earlier in this year. I'm going to do long division. You can probably do this with synthetic division. I'm just going to do it this way, even though it's probably less efficient. I think it's more illustrative. Okay. So first, as we, if you think back to when we did long division, we think what value of -4x what value when we multiply it by -4x gives us x squared? Well, that's going to be -1/4 x, right? So that gives us x squared. And what is -1/4 x times +4? That's just going to give us -x. Okay, so now what we want to do is subtract both of these. Right, I just want to make sure that I have the right equation. So when we subtract both of these, we see that we get 0. And then we get -12. And so obviously we can't do anything into 0. We can't multiply x by anything to get 0. So we're basically left with this remainder where we would say something like negative minus 12 over negative 4x plus 4, and yada, yada, yada. But this is sufficient information. This, even if you're left with a remainder, it's fine. We don't care about that. You just want to do this all the way out to the point where essentially you get this linear line. So something times x, and in this case, these x's canceled out, but you might also see it like a plus b, something like that, like plus 3 plus 2 minus 7, something along those lines. But this is going to be our slant asymptote. So we want to say y equals negative 1/4 x. Okay, perfect. We know that we don't have a horizontal asymptote. I'm just going to say our range is all real numbers. Okay, now we want to care about our y-intercept. So essentially, when we plug in 0 to our function, what do we get? And I'm not going to plug it in to here because that requires a bunch of math. I'm just going to look here and say, when we plug in 0, this x squared, this x minus x cancels, so we're left with negative 12. That's a 2. Over this negative 4x cancels when we plug in 0. So negative 4 over, negative 12 over 4. And that's equal to negative 3. So that means our y-intercept is 0, negative 3. Okay. So we have a bunch of information at this point, and we want to put that down onto our graph. So first, the asymptotes. Oops, that's my bad. We have an asymptote of x equals 1. So I'm going to draw a line right here. Oops, my bad. Okay, perfect. Great. And then we have a slant asymptote at y equals negative 1/4 x. So that means we're essentially, if we graph this line, it's going to look something like this. So I'm going to put some points here just so I can use them as references. And then I'm going to draw a line like this. Something along the lines of that. Okay, great. Now let's put down some of our points that we have. So we have a point at 4, 0, something there, negative 3, 0, something there, 0, negative 3, something there. Okay, great. And now we're at the point where we just want to start finding some points so we can get an idea of what this graph looks like. So I'm going to plug in 3 for x. And when I plug in 3, I don't know which one's easier. I'm going to just plug it in here. 3 minus 4 is negative 1. 3 plus 3 is 6. So negative 1 times 6 is negative 6. 3 minus 1 is 2. Negative 4 times 2 is negative 8. I think we said negative 6 over negative 8. And so that gives us positive 3/4. So I'm going to put this like right there. Okay, now let's plug in 2. 2 minus 4, negative 2. 2 plus 3, 5. Negative 2 times 5 is negative 10. 2 minus 1 is 1. 1 times negative 4 is negative 4. So 10 over negative 4. Ooh, Lord. No, sorry. Negative 10 over negative 4 is 5 over 2, which is 2.5. This is something there. Now, you can keep on plugging in more points, but I'm pretty much like, I've seen enough. That isn't a great graph, but I know it's going to look something like this. I'm going to do the same here. I'm probably going to get one more point. I'm going to plug in negative 1. And so negative 1 minus 4, negative 5. Negative 1 minus 4, negative 5, negative 1 plus 3, positive 2, negative 5 times 2, negative 10, negative 1 minus 1, negative 2, and then negative 2 times negative 4 is positive 8. So we have negative 10 over positive 8, so that's going to be negative 5/4, or negative 1.25. So I know we're going to have a point right there. And I'm sort of doing this all in my head. Maybe I've made a mistake. Just check. And you're welcome to slow it down, sort of see what I'm thinking. I'm trying to say this all out loud, so you can sort of understand my train of thought. But essentially, this is what our rational function is going to look like in this case. And I don't know. I'm not going to lie, looking at this right now, it looks sort of aesthetically pleasing. But yeah. Okay, so let's go on. Essentially, there's going to be other practice problems, but I'm going to go down to number 7. So try all of these. We've talked about, hopefully you can use some of these things I've talked about when we've gone through these two problems to help with some of these other ones. But I'm going to do number 7, and we're going to try this. Okay, so I'm going to call this f of x again. And first thing we want to do is factor. So we can see we want to factor out a 2 out of the top. So we're going to have 2 times x minus 1. And then we're going to try to factor our denominator. First thing I see is we can factor out an x. So I'm going to say x times x squared minus 4x plus 3. Now, how would we factor this quadratic? Well, what are two numbers that multiply to 3, positive 3, and add to negative 4? Well, that's going to be negative 3 and negative 1. So I'm going to have x, and then I'm going to have x minus 3, and then I'm going to have x minus 1. Okay, perfect. Now in this case, we again have an x minus 1 over an x minus 1. So we know we can cancel those out, and in this case, we're going to have a whole. Okay, so once we cancel this out, we have 2 over x times x minus 3. Perfect. Now, let's sort of graph this whole. And we graph this whole the same way we did above. We're going to plug in, or what value of what value of x are we missing because of this whole? 1, right? Because 1 minus 1 is 0, 1 minus 1 is 0. When we multiply all this out, we get 0 over 0, and that's undefined. That's why we have that whole. And so let's plug in 1 into this new equation. So we have 2 over 1 times 1 minus 3. Now 1 minus 3 is negative 2. 2 over negative 2 is going to be negative 1. So we have a whole at 1, negative 1. We have a whole at 1, negative 1. Perfect. Okay, so let's move on to finding these zeros. And so we find the zeros by setting our numerator equal to 0. 2 never equals 0. So we have no zeros or no x-intercepts. And that'll become apparent in a second. Okay, so now let's move on to vertical asymptotes, and that's when we set our denominator equal to 0. So when does our denominator equal 0? Well, we have to set each of these equal to 0, so x has to equal 0, and x minus 3 has to equal 0. When does x minus 3 equal 0? When x equals 3. So we have vertical asymptotes at 0 and 3. So I'm going to write that here. And this is also kind of interesting because you'll see we have two vertical asymptotes. Did we say negative 3, 3? No, positive 3. This is my bad. Okay, great. So our domain x cannot equal 3, and x cannot equal 0. Okay, great. Now, let's work on horizontal asymptotes. So let's look, what's the degree of our numerator? It's going to be 1, right? We have x to the first. What's our degree of our denominator? X to the third. So our degree of our denominator is greater than that of the numerator. So let's scroll back up here and see what case does that elicit. Well, that's going to be case B. Our degree of our denominator is greater than that of the numerator. So our horizontal asymptote is going to be y equals 0. And so that is why we don't have any x-intercepts. So horizontal asymptote is y equals 0. And so that means our range y cannot equal 0. All real numbers except for that. Okay, now, slant asymptotes don't apply because our degree of our numerator is not 1 greater than that of the denominator. So we move on to y-intercepts. And so essentially we just want to plug in 0. And we see, you can see it in two places now. X cannot equal 0, so we don't have a y-intercept either. Okay, so let's start graphing this. So we have a vertical asymptote at x equals 0. Something here. And then we have another vertical asymptote at x equals 3. Oh geez, I don't know why I did that. Sorry, this kind of takes a somewhat long time. Okay, and then we have another horizontal asymptote at y equals 0, so something like this. And then we don't have any points except for this hole. I'm going to still put that down. So we have a hole at 1, negative 1, which is right here. And that's valuable information. Okay, so we're at the point where we just want to start plugging in values. So I'm going to start with the negatives. So I'm going to plug in negative 1. And I think it's actually easiest to plug it into this function here. So 2 over negative 1 times negative 1 minus 3. Well, negative 1 minus 3 is negative 4. Negative 1 times negative 4 is positive 4. And so we have 2 over positive 4. That's going to be 1/2. So we have a point right there, which I just want to make sure of. Okay. So let me think of this. Sorry, just for a second. Okay, great. Now in this case, we're sort of stuck in somewhat of a predicament. I'd plug in 0.5, for example. So this might get a little wonky, but 0.5 times 0.5 minus 3. Well, 0.5 minus 3 is negative 2.5. And negative 2.5 times 0.5 is... we're plugging in negative 0.5. That's my bad. So negative 0.5 times negative 0.5 minus 3, that's going to be negative 3.5 negative 3.5 times negative 0.5. And so that's going to give us positive 1.75. So 2 over 1.75 is going to be about, 8/7, which I'm just going to say is a little bit over 1. I'm going to put a point right there, something like that. And then, maybe just because, we should plug in another point. Let's say let's plug in it really isn't that important. But let's plug in like a negative 3, for example. Negative 3 minus 3 is negative 6. And so negative 6 times negative 3 is going to be positive 9. 2 over 9 is 2/9. Basically, all we care about is it's pretty close to 0. And so we start to see this pattern where we have this shape develop. So it's going to look something like that. Okay, now I'm going to move on to this part. So when x is greater than 3. So I'm going to plug in 4. So 4 minus 3 is 1. 4 times 1 is 4. 2 over 4 is 0.5. So we're going to get something like this. That's pretty interesting. That's the same thing over there. Okay, so now I'm going to plug in 3.5. So 3.5 minus 3 is 0.5. And 0.5 times 3.5 is going to be 1.75. So again, same thing as before, 1.75, 8/7, basically just a little bit above 1. So something like that. Wow, this is pretty interesting. Now I'm going to plug in, sorry, it's not interesting. It doesn't matter. Okay, whatever. Now I'm going to plug in 6 for an x value. Now 6 minus 3 is 3. And 3 times 6 is, sorry, let me make sure I'm getting this right. Yeah. Okay, 6 minus 3 is 3. 3 times 6 is 18. So we have 2 over 18, which is 1/9, basically 0. So something like that. Let me just make sure when I did this before. I don't know if I did this before, if I said that point before was negative 3 minus 3, which is negative 6. Negative 6 times negative 3 is 18. 2 over 18 is 1/9. I don't know what I did before, but it's 1/9 instead of 2/9. It's going to look the same on the graph. But yeah, sorry about that. I think I made that mistake. Okay, so we have enough points where we start to see this pattern form. Okay, and we notice that it's actually the same as what's happening on that left side, but this isn't always going to be the case. So do plug this in, because this is actually kind of I would not say a rare occurrence, but you'll see a lot of times where we have something down here instead. So just plug in a bunch of points. And then let's do this middle section. So this middle section is kind of weird, or it's not weird, but it does not obey all of the same rules as some of these curves on the outside of these asymptotes do, at least sometimes. So what we just want to do is start plugging in values in between here. So let's plug in 2, for example. Well, 2 minus 3 is -1. -1 times 2 is -2. 2 over -2 is -1. So we see something here. Okay, now I'm going to plug in 1.5. 1.5, let me just make sure what I just did is correct. Yeah, I'm good. Okay, so 1.5 minus 3 is -1.5. And -1.5 times 1.5 is -2.25. 2 over -2.25, we don't need to exactly know what that is, but we know that, I said 2 over -2.25. We know that the numerator is slightly less than the denominator, so I know it's going to be a point up here like that. So at this point, I'm just going to plug in some other points just so I can be sure. So I'll plug in 2.5, for example. 2.5 minus 3 is -0.5. -0.5 times 2.5 is going to be -1.25, or -1.25. Now -1.25 over 2 is going to be -8 over 5, which I know it is not quite 2, but it's close. So I'm going to put a point right here. And if you plug in 0.5, you're going to see that it's the same thing. And so we start to see something that looks like a parabola, but is not. It definitely is not a parabola. Start to form down here. Something that looks like that. Okay, great. Now, something I will say, wasn't this case in this problem, but it will happen in other cases. You might see something that looks like a cubic, or most of the time it's something that looks like a cubic, or it looks sort of like this upside down U, like a quadratic. Although they're not cubics and they're not quadratics, they have these asymptotes. They behave differently. But sometimes you'll see that we cross over this middle boundary, this horizontal asymptote, and that is fine. That happens. But that pretty much only occurs when we have these middle sections. It won't cross over boundaries out here, but sometimes in the middle, some wonky stuff can happen. And that's pretty much all. So obviously there's quite a few problems that I did not go over today, but hopefully you can do those on your own, get some more practice with graphing these rational functions. But in the case that you get stuck, or you have some questions on some of these other problems, or just graphing rational functions in general, feel free to reach out. I'm happy to help. Just go to your teacher. They're knowledgeable on this subject. They should be able to help you. Also, I'd say reference your peers. I can almost guarantee in pretty much every single class you take, there's going to be one kid that pretty much knows what you're doing. And some friendly piece of advice is befriend that person. And whenever you're in trouble, just ask them. I've definitely done that a few times, and I've made some good friends along the way by doing that. So yeah, ask your peers, go to the tutoring center. You can rewind this video, slow it down, listen to it however many times you'd like, if in the case that it is helpful. And yeah, use the internet, use whatever resources are available to you to sort of answer your question or get you unstuck in some way. Okay, hopefully this was helpful. And yeah, have a good day. Bye.